Hey everyone, welcome back. Today we're pulling back the curtain on the two most important gears in the entire generative AI engine, tokens and embeddings. This isn't just going to be a technical deep dive. We're going to show you that AI doesn't actually read your words at all. It maps them. And trust me, understanding that changes everything.
So let's just start with the biggest question right off the bat. When you type a prompt into an AI, what is actually happening? I mean, how does a machine that only gets ones and zeros possibly grasp the nuance, the intent, or even the poetry in what you write?
Well, here's the kicker. They don't. At their very core, computers are just unbelievably fast calculators. They don't understand words or feelings or concepts. They only understand numbers. So how in the world do we build a bridge between our world of meaning and their world of pure math? That's the problem we're going to solve today.
All right, let's dive into the first part of the solution. If a computer can't read a whole sentence, we have to break it down into pieces that it can handle. We need to find the fundamental atoms of AI language.
Before we connect this to AI, just picture this in the real world. You're looking at this incredibly detailed Lego castle. It looks like a single cohesive thing, right? But your brain instantly knows it's not one solid piece. It's built from hundreds, maybe even thousands of tiny, standard bricks.
That process, that mental act of breaking down the castle into its individual bricks, is exactly what tokenization does for language. It's the very first and absolutely crucial step where an AI smashes your sentence down into these manageable little segments, these Lego bricks called tokens.
And what's so fascinating here is that a token isn't always a full word. It can be a subword, like breaking tokenization down into token and ization. This is incredibly efficient for handling complex or rare words. The most advanced method, called byte pair encoding or BPE, actually learns the most common character combinations in a text and just uses those as the tokens. This means it could tokenize literally anything, from English to emojis to other languages, without ever running into a word it doesn't know.
So if you're ever wondering how this all translates to, say, cost or context window limits, here's a great rule of thumb to remember. For English text, about 1,000 tokens is roughly 750 words. It's basically the currency of large language models.
And this history is just wild. The core algorithm here, byte pair encoding, wasn't even invented for AI. It was a data compression algorithm from 1994, designed simply to make computer files smaller. It took over 2 decades for researchers to realize that this clever method of finding and merging common pairs of characters was the perfect way to build a vocabulary for a machine.
Okay, so we've got our Lego bricks, we've broken the language down. But a pile of bricks is just a mess, right? It's meaningless without a blueprint. The next step is to give each of these tokens an actual identity. This is where the AI goes from just seeing words to truly understanding their meaning.
Let's set up another analogy. Imagine a massive, invisible map of a city. On this map, every single location, a coffee shop, a library, a park, has a precise set of coordinates. But here's the magic. The map is organized by meaning. So all the coffee shops are clustered together in one neighborhood, and all the libraries are in another. On this map, being physically close literally means you're similar.
That city map is exactly how embeddings work. Each token gets turned into a long list of numbers, a vector, which acts as its coordinate in this high-dimensional meaning space. This lets the AI do something that feels like magic, vector arithmetic. You've probably heard of the classic example. You take the vector for king, you subtract the vector for man, and you add the vector for woman. And the closest point on the map is, you guessed it, queen. The AI gets the relationship without ever knowing what a king or a queen actually is. You have to understand, this was a massive leap forward from the older models. Before embeddings, we had this thing called a bag of words approach. It literally just counted how many times words appeared. That meant it had no idea what the difference was between the dog bit the man and the man bit the dog. It had zero concept of order, and words like happy and joyful were treated as two completely separate, unrelated things. Embeddings fixed all of that. But there was still one huge problem left to solve. Words can have multiple meanings, right? So how does an AI know if you're talking about a riverbank or a money bank? Well, that brings us to our next big idea, context. So, consider this first sentence. Here, the word bank obviously refers to a financial institution. Its neighbors, the words around it are withdraw and money. But in this sentence, the exact same word, bank, has a totally different meaning. Now its neighbors are river and sunset. An early model would have given bank the same coordinates in both sentences, which would be like putting a coffee shop right in the middle of a library on our city map. It just creates total confusion.
This is where modern models, like the ones that power Google Search and ChatGPT, do something amazing. They use what are called contextual embeddings. They basically act like chameleons. The vector for bank doesn't have one fixed spot on the meaning map anymore. Instead, it actually shifts its position based on the words around it. When it sees money, it scoots over to the finance neighborhood. And when it sees river, it moves over to the nature part of the map.
So how does the model know which neighboring words are important? Well, if you look under the hood, there's this really powerful engine running. And to understand it, let's picture a classroom. You've got a teacher giving a lecture. And they don't just read from a textbook, right? They pause, they raise their voice, they gesture to emphasize the most important points for the students who are taking notes.
That teacher-student dynamic is a great way to think about something called the attention mechanism. For every single word, the model asks a question called the query. So for the word it, the query might be, what does it refer to? Then it looks at all the other words, and each one has a little label called the key. The word animal has the key noun. The model sees that animal is a really good match for the query about it, so it pulls the meaning, or the value, from the word animal and connects it to it. That's how it understands all the complex relationships inside a sentence.
Okay, so the attention mechanism is incredible. It looks at all the words at once to figure out these relationships. But that creates one last little problem. It forgets the original order of the words. To fix this, the model adds what are called positional encodings. Just think of them like simple number tags or little stickers on each Lego brick, telling the AI exactly where it belongs in the sequence. This is what stops "the cat ate the mouse" from becoming "the mouse ate the cat."
So where is all of this going? This entire architecture of tokenizing and embedding is now being used for way more than just text. We're moving from interpreting language to interpreting reality itself.
The future is completely multimodal. For example, vision transformers now treat images just like text. They slice an image up into patches, which are basically visual tokens, and then they read that visual sentence to understand what's in the picture. And it's even moving beyond sight. Researchers are now developing digital olfaction, where the chemical makeup of a smell is turned into a scent embedding, literally allowing an AI to identify and categorize smells. This entire field is just constantly being refined to create more and more accurate maps of our world.
So the takeaway here is really profound. The fundamental architecture that was designed to understand language is now being used to give machines a sense of sight and, yes, even smell. The next frontier isn't just about processing our data, it's about processing our sensory experience.
If this has sparked your curiosity and you actually want to see this stuff in action, there are some incredible tools you can play with right now. You can use OpenAI's Tokenizer to see exactly how your own sentences get broken down, and if you're ready to start building, you can explore amazing libraries from Hugging Face and Pinecone. Don't worry, we've put links to all of them down in the description.
So, from text to images to smells, this architecture is creating this incredible high-dimensional map of our entire world. It just leaves us with a pretty fascinating final question to think about. What part of the human experience, emotion, creativity, maybe even intuition, will AI learn to map next? Thanks for watching.